The second type of organic mechanism that we look at is addition reactions. An addition reaction is one in which two or more molecules react together to form a single molecule. Alkenes are used as raw materials in a lot of industries, one example being the manufacture of plastics. Alkenes are far more reactive than alkanes due to the carbon-to-carbon double bond. This bond is electron rich and therefore can donate electrons in a reaction. It is made up of a sigma and a pi bond. Remember that all single bonds are sigma, and then you add on pi bonds by adding in a double or a triple bond. The pi bond is weaker and more easily broken, which allows a double bond to undergo reactions. There are three reactions with ethene that you need to know the mechanism of. The reaction of ethene with chlorine, bromine, and hydrogen chloride. The good news is that it's the same mechanism for each of them. You just have to be able to write it out specific to whichever one you're given in the question. There's also two other reactions with ethene, hydrogen and water, and you just need to be able to identify the products of that reaction. You don't need to actually write out the mechanism. So we're going to look at the general mechanism using the molecule XY, and then depending on whether you're given chlorine, bromine or hydrogen chloride, you just change X and Y to whatever molecule you need. Step 1 in our 4-step process is polarization. We know that polarization is going to be talking about creating poles. The double bond, as we mentioned in ethene, is an area of high electron density. That means that there's a lot of negative charge there. As the XY molecule approaches, it's going to be polarized. The electrons in the XY bond are going to be repelled by the electron density in the carbon-to-carbon double bond, giving us an XY molecule with a partial positive end and a partial negative end. Step 2 is heterolytic fission. Remember, fission means the breaking of a bond. So this strong induced dipole in the XY molecule is going to be so strong that it's going to cause X and Y to split up into their ions. Now, heterolytic fission might remind you of homolytic fission, but it's the opposite. So heterolytic fission is where a bond is broken and the two products formed are different. Homolytic fission was where we had two identical products formed. Step 3 is the formation of the carbonium ion, where the positive ion, in this case X+, that was formed in step 2, attacks the carbon-to-carbon double bond. What it's going to do in order to make itself stable, it's going to form a covalent bond to one of the carbons in the double bond. However, X+ does not have an electron to use to form this bond. So what's going to happen is the X+ is going to bond, if we name our carbons carbon 1 and carbon 2, it's going to bond to carbon 1 by taking these two electrons from the pi bond. But what you'll notice, and it forms this bond, to carbon 1. What you'll notice though is it has taken an electron from carbon 2. Anything that loses an electron is going to have a positive charge. So carbon 2 is now positively charged, and this species here as our product is called the carbonium ion. It's an intermediate because it's formed during a reaction, but you're never going to get it as a product. It's very unstable, and so we'll see it react now in the next step, which is ionic addition. This is where we go back to step 2 and we're going to take our Y- that was produced in step 2, and this time the Y- is going to attack the carbonium ion. The result of this is a bond between carbon 2 that was positive and this Y-. So both of them now have satisfied their octet rule. This process is called ionic addition, as the ions are added across a double bond, one on either side. You can see that here. X is added to one side and the Y is added to the other. Our summary here of the whole process is put together in one slide for you in order to make it easier to take down your notes. Since we can't produce the carbonium ion, or we can't isolate it, we need to provide evidence for the validity of this mechanism. The evidence comes to light when we add other negative ions to the solution. When we do that, a mixture of products is obtained. When we went through our example using the XY molecule, the only anion present was the Y- ion. So we only had one option for our product. The same goes here if we have bromine and we're adding that to ethene. We only have Br2, so there's only Br- going to be present. And so we only have one option for our product, this one that I'm pointing to here. However, if we carried out this exact same reaction, but we added in a small bit of salt water, two other compounds are formed. Because from the salt we get Na plus and Cl minus, and from the water we get H plus and OH minus. Now we have two more negative ions that can attack the carbonium ion and react with it other than the Br-. And so there's two other products here that can be formed. One with bromine on carbon 1 and chlorine on carbon 2, and the other one with the hydroxide OH ion on carbon 2. This provides us with evidence that the carbonium ion does form, that there's a two-step process where a bromine is added first and then a negative ion is added second. The syllabus sums up this evidence nicely in a quick sentence here, where it gives the names of the products. So we have not highlighted is 1,2-dibromoethane, what we would expect. So that's this product here. The 2-bromoethanol is in the yellow, highlighted in yellow, and the 1-bromo-2-chloroethane is highlighted in green. Another example of an addition reaction can be polymerization. Polymers are long chain molecules made up of small repeating units. The ones that we're going to look at now are addition polymers because they occur when an alkene undergoes an addition reaction with itself. All of the atoms in the original alkene are used to form the polymer. So there's no other product. There's no byproduct, no co-product, just the polymer. And what we get is long chain hydrocarbons. The first example is the polymerization of ethene. This is where you have lots of ethene molecules that are going to undergo an addition reaction together to form a long chain hydrocarbon. We can show how this happens in a similar way to how we showed how the substitution reactions happen. I can use a single-headed arrow to show the movement of my electrons, where they're going to go. This double bond is going to open up and allow each carbon to form another bond. So there's going to be one electron from that carbon, one electron from that carbon, forming a single bond between them, and the same over here. Now, as you can see from my products up here, it's important to show that this molecule is not complete here. We have to show that there is also space here for another bond to be created there. We're only showing a small section at the moment. And in that product, you can see up here that there's three things I've put a box around, and that's my repeating unit. So it's the same thing repeating over and over again. The repetition of this repeating unit is what creates the polymer. It's important to note that the end units are going to look different. The very end of the chain is going to look slightly different because whatever carbon we have on the end is going to have a hydrogen attached to it to complete its outer shell. You also need to know some uses of polythene as we're here. Some examples would be the manufacture of lots of different plastics like cling film, plastic bags, plastic bowls and lunch boxes. Another example would be the polymerization of chloroethene to make PVC. Again, this is done in the same way where we take the double bond in the chloroethene molecule, we open it up, and that allows us to create some more single bonds over here that we didn't have before. Again, it's important to show that the molecule is not complete here. We don't want to show the molecule being complete because it's not. So you have to show those extra bonds sticking out at the end. It's also helpful here to put some brackets or a box like I did in the last one around your repeating unit. We can see here that my 2 repeating units, I'm drawing the little square brackets around them here now. So that's my repeating unit. The polymerization of propene to make polypropene is done again in the exact same way. We open up the double bond to create some single bonds between the molecules, and that gives us our longer chain hydrocarbon then. If we were to just look at this one here, our repeating unit would be this one. What you'll notice here as well is that the propene is drawn in a different way to what we would usually draw it. What we do here is we draw out the double bond and everything is put on then as if it was a hydrogen. So the CH3, the third carbon that's not part of the double bond, is put on as kind of like a side chain, or drawn in the same way as a hydrogen would be, just for the ease of showing what our repeating unit looks like in the product. So the 3 that we just went through there are the 3 polymers of ethenes that you could potentially be asked about. Ethene making polythene, propene making polypropene, and chloroethene making PVC, or the full name for that would be polychloroethene. Just to point out to you here the symbols that they're using. So the N means here any number of ethene molecules is going to make a hydrocarbon chain with that same number of repeating units. All that's going to be different is that there'll be a hydrogen on either end to complete the molecule and make sure it's stable. Here's a handy summary of all of the alkene reactions that we've looked at. If you have any questions on these, please do let me know.